more advanced post-processing operations, structural, statistical, and database. So structural, in particular, we can compute dissimilarity matrix. So for instance, with a spectrogram, we can compare each frame, Vi, with each frame, Vj, and we compute a matrix with all these distances. So it's symmetric. And we see in the diagonal actually the comparison of each frame with itself. So of course the dissimilarity is 0. So this is a dissimilarity matrix. For the dissimilarity we can specify also the distance, cosine by default. So the similarity is computed from that dissimilarity by an operation of transformation, in particular by default exponential negative. So now in the diagonal the similarity is very high, so red colors and so on. What is used currently in the toolbox is simply if we can see from that similarity matrix some particular transition between states that will indicate segmentation. And we can see here that indeed there are these squares, red, reddish or yellow, or light blue, that are one after the other along the diagonal that seems to indicate this change of state. So in order to see that clearly, we compute novelty curve. We first have this kernel where we have the same succession of two squares, one lower left and upper right. It's Gaussian kernel, and now we perform a convolution of this kernel along this diagonal, and we obtain a novelty curve. We see here, depending on the size of the kernel, we can have different analysis. For instance, very detailed analysis. With a small kernel, we can see very precisely these different very red squares here. Whereas if we take a large kernel, then we will see more these light blue succession that are not so clearly seen here. But here we can see that there are these transition between different moments in the piece. So we can now estimate the local maxima and can be considered as point where there is segmentation. So now we can segment based on that. And so there are these syntax, novelty is the default, and you can specify the feature you use for that and so on. As shown before, you can compute a spectrum for each segment, and you can compute the similarity matrix between these segments. Clustering. So now, for instance, we have these segments, and we can compute feature for the different segments, and if successive segments are very similar, then they are clustered together. This is based on k-means clustering. Another kind of clustering is you have a frame decomposed signal. You can try to find, for instance, 4 different classes representing your different frames. You can see that some of the frames are centered around one class. The centroid of this class can be the description of it. So now we can represent this spectrogram by replacing each spectrum of each frame by the representant of that class. And now you see that you have some simplification that is quite interesting to see. So you can change the number of clusters. Okay. For statistical analysis, you have basic statistics, mean, standard deviation of any of these curves, frequency of the periodicity in the signal, amplitude and periodicity entropy. Then you can compute histogram of any of these data. Zero crossing rate can be computed from any curve. Then centroid, spread, or mean variance, dispersion, standard deviation, skewness of the curve, kurtosis, and flatness. So entropy here is based on the Shannon entropy, but we use it only to see if the curve has prominent peaks or not. In order to do that, we need to consider the curve as a probability distribution. So for that, we need to remove the negative values and say that the sum is equal to 1. And we compute the Shannon entropy of this curve, but because usually the entropy is dependent on the sequence length, we can use a relative entropy like this. And now, if you have high entropy, it means that you are not sure what will be the possible outcome. So you have a flat curve. And reversely, if you have low entropy, it means you can see there is a peak. But we use just this, the fact that there is a flat curve or a curve with a prominent peak. So now we can also compute all these possible features, most of them. And there is these MIR features that will do that optimally. And structures and along this dimension. In the output, you have one field dynamics with only one subfield, and then one field rhythm with these two subfields, and so on. And then you can compute MIR features for your big folder of files and get the statistics automatically. So it's just one line and then lots of computation, number crushing. And actually, for instance, there are some other options where you can write during all this computation, write the result directly in a file, little by little. So if it crashes, you keep the data. And then you can export also with MIR export. So you give the file name and then a succession of data that you have computed. You can export to text file and to ARFF. Then you can use for data mining using Weka. Or you can export directly in the workspace in MATLAB. It's a first step toward trying to have a tool in the MIRtoolbox for statistical mapping called MIRmap, but we plan to show more advanced tool later. But basically, for the moment, you have a folder file. Let's say you ask some subject to rate this file according to one particular aspect in music, subjective aspect, emotion, pulse gravity, and so on. You store the ratings in a text file. Then you can compute these features for the same folder file, export that, and then there is this MIRmap operator that we try to find some connection between the ratings and the features. So try to make a model that will predict according to the features. This is first attempt. So for the moment, let's say you have a lot of features, it will select some of them using particular, for instance, stepwise regression, and you will see the best feature. And in this graph, in the x-axis, you have the correlation between the predictor and the rating. And you see the p-values in color, so the significance of each of these prediction, and so on. To be continued. Then, let's say database analysis. For instance, we can perform basic classification. So you can say, I have this folder, and using MIR label, you assign a label to each of these files, and then you can try to build classification and see what will be the predicted class for another folder. This is a syntax, so you have to specify which feature you want to use for this prediction. And you can also use a set of features, and there are different classification strategies, but they are very simple in a way. Okay, nearest neighbor, Gaussian mixture model. But for advanced data mining, it's better to use Weka for that. Then we can compute distance between features. Let's say you have two band spectrum. Then you can compute the distance and specify the measure, for instance, cosine. Then it will return the result. And if you have now clustered data, as I explained previously, so you have clustered this file around 16 different classes, and same for this one. Now you can compute the distance between them using Earth mover's distance. It's in the documentation. And if now you have one file on one hand and a folder of file on the other hand, then you can compute the distance between that file and all these successive files. So you see here the result. And now, from that, you have a simple MIR query. The first file was a query, and what will be returned is the file of the other folder ordered with respect to the distance. And you can play this retrieval.